All right. So I just wanted to start. I passed out. I think everybody should have got the right quiz. Did I get everybody right? It's not easy, guys. I recognize all of you if you're not wearing masks, but such is life. So I just wanted to go over the quiz, just kind of some general comments. People did well as expected. The most common grade was an 8 out of 10. So if you got an 8 out of 10, you have good company. That's most everybody got. But there were some 10s, which is good too. Drawing streamlines, those are going to be the lines that are tangent to the velocity field. And the cool thing is these are, so the white streaks, I guess, or the black streaks, are all going to be streamlines. So if you traced, I think, again, people got that right. The part that was tricky, and I apologize, it was tricky, was question number 2. So this is where if you got an 8, this is where you lost 2 points, along with most other people. So the streamlines, if the white streaks are streamlines, that means they are tangent to the velocity. So if they're tangent to the velocity, there's only one direction the velocity could be in. It has to be tangent to those lines. But that's just the direction, right? The velocity is the speed and the direction. So you could have lines like that, or you could have lines of a different velocity, right? So there are different velocities, different speeds, but they all have to be the same direction. So just to kind of drive home the point that what streamlines are showing us and what they're telling us is the directionality. They're not directly telling us the speed, but they are directly telling you the direction, directly the direction. So that information is like easily visible. We'll actually dig in later on, quite a bit later, dig into some of the more math of streamlines, which will be kind of fun, and we'll see there's actually a lot more information that you can get. You can get speed information just from the streamlines, but we haven't figured out how to do that yet. And that won't be till quite a ways down the line. But hopefully this gives you somewhat of a taste of like visual. There's a lot of information in just a visual picture like this, or just a visual experiment that you can actually extract out. The last one, and I think everybody got this, is the path line at B. It's going to, zoom down along its little trajectory as shown there. Okay, so the key points, key takeaways. In steady flow, streamlines and some of these path lines and streak lines, those are all going to be the same thing, right? We can do experimentally, we can make path lines and streak lines visible by different methods. That's going to make the streamlines visible, just like you drew. But then streamlines give the shape, but not directly the speed. There are other things that we can do to get some of that information out, which we'll learn about later. Then I just wanted to just share some of the joy that I had while looking at some of these. Some of these were quite fantastic. I like the Ankylosaurus. The T-Rex and the Ankylosaurus are definitely the top dinos. These are some good ones. This is art, guys. That one was good. That was solid. Some people need some help following instructions, but it's a good question. And then I said to draw dinos. This wasn't that hard. But then this is the best in show. I'm not going to name who it was, but you can out yourself if you want. Overall best dino. This one was my favorite. It made me the most happy. So thank you. I'm recording this lecture, so we'll have the video. So anyway, thank you for playing along. Yeah, are we having art prize this year? So you can maybe enter it. You do like a big print of that dino. All right. Pardon? Why did we do that? View video. Ta-da. There we go. Okay, thank you. So today, we're gonna pretty much wrap up fluid statics today. At least that's the goal. What we talked about last time regarding fluid statics, we kind of derived some of these basic equations, not last time, but the time before on Friday. Then we said, okay, one system that we can use these to help understand is pressure measurement devices like manometers. And you just get kind of the feel like, okay, so right, I mean, some of this stuff is really basic. You go down in the fluid and the pressure goes up. The way that I typically like to think about it, and this isn't it's not an inaccurate way to think about it, but the pressure goes up. What is the pressure? It's the weight of the fluid sitting on your head, right? That's the pressure. So it doesn't matter what's happening, like what the shape, it's the total weight that's sitting directly over top of your head. Okay, that's fairly basic. We're going to try to get into more like engineering type stuff, more like statics-y type stuff today in class, so we can ask more interesting, more complicated questions about what's happening in different fluid statics problems. So we're going to look today at forces. Forces on submerged surfaces. Okay, so if you have something underwater, you're designing a dam, you're designing a submarine, you're whatever it is, if you have something underneath a fluid, what do the forces look like? So we'll just pick kind of a simple example to do some of the background calculation and derivation on to be able to look at what this looks like. We'll say that we have there's a dam, and in the center of this dam is like a gate. So a lot of dams will have a bypass where you can let water down like a chute down to the bottom, and there's going to be a gate that opens and closes that bypass. So that's somewhere underwater. It has a gate that opens and closes, and we want to say, what are the forces pushing on that gate? Right, we wanted to design, what are the forces look like? What do those look like? So we would want to know a couple things about this. We would want to know the force magnitude. We would want to know the force direction. And the moment about, say, like we have a gate that opens and closes, maybe there's a hinge that's closing it. We might want to know the moment about that location. So the moment, or the call it the force location, or the resultant force location. Right, so just like as a super quick refresher, in statics, what we would do is something like this. We might have something, say there's an axis or a location, like a joint, a hinge, something like that. And there's this beam, and we have, say, three forces, F1, F2, F3, which are acting on that beam. And we could characterize these by the location. So there would be X1, X2, x3. In order to solve this more easily, we could simplify this picture to a single force acting at a single location, right? So we would have maybe, I don't know, right there, we'd have a single force, the resultant force, acting at a single location, which we'll call x prime. So the resultant force Fr equals F1 plus F2 plus F3. It's just the sum of all the forces. And the location, the moment, so the same moment about point B. So we would have like x prime Fr would be equal to x1 F1 plus x2 F2 plus x3 F3, right? This is all coming back to you now? Okay, fairly basic stuff. So the issue with what we're trying to do is we don't have just like three forces acting at three locations. We have a pressure field, right? Pressure is changing with depth. That pressure is giving rise to force on the gate. So we have to figure out, okay, how does all this stuff fit together? Right, so pressure is going to go up as we go deeper, and maybe the gate, as I drew it, is at an angle, and how do we fit all the geometry and the moment stuff, and how do we fit all that stuff together? Okay, so what we'll do, I'll redraw things so that we have a kind of a fresh picture. Otherwise my picture is going to get really messy. So we have our water. We have the dam, right? Gravity is acting straight down. And we have, I guess down here, this is our that's our gate. So that's the thing that we care about at some distance underwater. The very first thing that we have to do is place axes onto our system. So you might be, right, there are kind of two logical choices. One would be to put them so that like down is in one direction of the, like maybe that's the Z direction or the Y or whatever. It's like in line. So straight down is in line with one of our directions. It turns out that makes our math a little hairy. It's easier mathematically. We're going to have to do less sines and cosines and stuff to put our direction in the plane, to put our axes in the plane of our object. So we're going to place axes in the object plane. Right, so we're going to have, say, we'll put the origin at the surface with 0, 0. You don't necessarily have to put 0, 0 at the surface. There are other ways to do it. We'll do 0, 0 at the surface for right now. So that would mean that this is one direction, that's another direction, and then in and out of the page is our third direction. So this would be, we'll call that Z. Down deeper into the water is Y, and in and out of the page is X. Okay, so pressure always exerts a force normal to the area it's acting on. So if pressure is pushing on something, it always pushes normal to the area. So the direction of the force, as we've drawn it, this would be that FR is in, I guess, minus K hat direction. Right, so FR is pointing into the gate. Right, it's pushing in on the gate. The magnitude of this force, we'll look at the magnitude first, and then we'll look at where is it actually on the gate. The magnitude is going to be, right, just like it was in stat, it's going to be the sum of all the forces. So the magnitude of FR is the sum of the force acting on that gate area, acting over the entire area of the gate. So the force at any one point, it's not quite this easy, but right, force is pressure times area. Now the challenge is that our pressure is not constant. So we can't just say the pressure is, 100 megapascal, so, or 100 kilopascal. So, it's 100 kilopascal times the area of the shape. Because the pressure is changing at the top of the gate, that's in shallower water. The bottom of the gate is in deeper water, so it's going to have a difference depending on where we are. So let's figure out how we do that. So we're going to look at every little section of the gate individually, and then we'll add all of those up. So we're going to look at differential sections of the gate, and we'll add them up by an integral. So a differential force is equal to the pressure times a differential area. Then we can add these up, right, which is what we do when we do an integral. So our resultant force, FR, is the integral over the area of our shape of P dA. This pressure changes with depth. So this is going to be equal to the integral over the area of P naught plus rho G H dA. Right, that's our function for pressure. H is the depth underwater. So the depth underwater is going to be, if we look back up at our picture, if we move in the y direction, we are going deeper underwater, but it's not like straight down. So if we go 1 meter in the y direction, we don't go 1 meter down because we're going on an angle. So we have to take that angle into consideration. So if we look at this angle here as theta, the angle between our axes and the surface of the water, right? If that angle is 90 degrees, then yeah, we are going straight down. If that angle is 75, we're not going totally down. So a meter in the y direction is not a meter down. So those are connected by how far we go in y times sine theta. That's how deep we're going. So this is equal to, that's a bad equal sign, equal to the integral over the area P naught plus rho g y sine theta times dA. Okay, now we have to integrate this. Some of this is really easy, some of this is less easy. So this is going to be, if we split it apart into like two different halves because of the addition sign, we can integrate the first part, that's P naught A. And then we can integrate the second part. Most of that second term, this second term, most of that is just a constant. Most of those are constants, right? Density, constant. Gravity, constant. Sine theta, constant. Y is our dimensions. Okay, so Y we can't, but let's pull everything else out. So this is equal to plus rho g sine theta times the integral over our area of y dA. Okay, this integral, does anybody recognize it? If you do, I'll be kind of impressed. If you don't, I'll be, I guess, neither impressed nor unimpressed. Okay, nobody recognizes that integral? It's fine if you don't. So that integral, this guy, the integral over a of y dA, this is equal to yc a, where yc is the centroid of the shape. Does everybody know what I'm talking, when I say when I mean the centroid? Right, it's the it's like the geometric center of mass. I think that's you guys are all used to thinking about center of mass. This is the geometry version of center of mass. So it's if everything is constant density, it's just like where is the center of the shape. So if you had something, again, like this, right, if that's y and that's x, that would be xc, yc. That would be the centroid of the shape, right in the dead center of that shape. If you had a shape like this, I don't know why you would, but if that's your shape, right there would be xc, yc. Right, it's the center of the area of the shape. So it's something for simple shapes, you can just like draw exactly where it is. There are other techniques to actually finding it that are more complicated that we're not going to go into in this class because that's not totally the point. We'll focus on simple geometries and simple shapes to get some of the fundamental ideas down. But that's what it is. It's the centroid. So what does that mean? Okay, so then our equation for FR would be equal to P naught A plus rho G Y centroid sine theta times A. Or we could rewrite it P naught plus rho G y centroid sine theta A. And I rewrite it that way because then this thing, this is simply the pressure at the centroid of the shape. Right, YC sine theta, that's the depth of the center of the shape. So P naught plus rho G, height underwater of the centroid of the shape. So this, our resultant force FR equals PC A. So this is PC. So this should, at least when I draw the picture, it should hopefully make at least some sense, right? So if we imagine our gate here, there is the centroid. That centroid is, so here's the water. That is the, we would call HC, the depth underwater of the centroid. That's YC sine theta. Again, I guess we would have our axes up here, so that's Y, B, Z. If we think of what the pressure is doing, pressure is going up as we go deeper. So the pressure is going to look something like this. Right, so the pressure is going to be going up. So there's going to be an increasing force as we go down on the object. But the right, it's all linear. So if we took like what is the average pressure times the area, well, like if you wanted to take the average, you could take right the pressure here, and that's going to be, so like there's a, you know, the amount extra that you get when you go deeper is the amount that you lost because everything is just linear. So all that you're saying is that the pressure at the geometric center is the average pressure. And that works because everything is linear. Okay, the more challenging part is to figure out where exactly that resultant force is acting. If you look at this picture, right, it's going to be the sum of the moment, like the moment has to be equal to the sum of the moments. So it's going to be weighted so that it's not acting exactly at the middle. It has to be acting somewhat below the middle, somewhat deeper than the middle of the shape because pressure is going up as we go down. So, right, like it's weighted so that we have more force on the bottom of the shape than we do on the top because pressure goes up as you go down. So that will be our next job, is to find the location of FR. Right, so we need, and we'll call this X prime, Y prime. So that prime notation, so X prime means the X location of that resultant force, Y prime is the Y location of the resultant force. We can split it and look at just the x and then just the y. We can look at those two things separately. So if we looked at the so moment about the x-axis, that would be y prime FR, right? Because so the rotation is about x. So you're saying like, right, if we have a force pushing where that blue is, there's going to be the propensity to rotate about the like in and out of the page axis. So it's going to be the moment about the x-axis is this equals the integral over the area of y p dA. Okay, and then so the moment about the y-axis is similar. Okay. So the pressure could be a function of y or x. So pressure is not necessarily a constant. Pressure could be changing because we could be going deeper. So this x prime and y prime, that's the location that we're trying to find. We'll look first at the moment about the x-axis, because that's the one that's tricky. So our strategy is just like it was before. So we'll plug in pressure as a function of y. And integrate. So we'll plug that in and integrate. So we have y prime FR is the integral of A, and then I'm going to plug everything in. So that's y. So pressure as a function of distance in the y direction. That's the same as what it was before. Rho g y sine theta dA. So it looks very similar to what we had before. Same pressure. Let's break this integral up into its two different parts around the plus sign, and then we'll look at each one individually. This is was the integral for A of y p naught dA plus the integral of rho g sine theta y squared dA. This first integral here, that integral is the integral A of y p naught dA. We can pull the p naught, that's the pressure at the surface or pressure at the origin. Y dA. And then we can say, ta-da, we've already actually solved this before, so that equals p naught, that integral, the integral of y dA, we said that was the centroid yc times the area. Okay, this second integral we'll look at down here. So that's the integral for A of, so that's rho g sine theta y squared dA. We'll pull out everything that's a constant. rho g sine theta. And then we have the integral of y squared dA. Then kind of like we did in the last thing, we said we know the integral of y dA was the centroid, the geometric center of the shape. The integral of y squared dA, we'll say, aha, I already know what that is. It's not the centroid, it's not the center of the shape. This all has to do with rotation. So what might this integral be? What's something that's like shape dependent that has to do with rotation? Like the moment of inertia of a shape. Right, so different shapes have different moments. So this is the, this one, y squared dA, the integral equals, we call it IXX, which is the second moment of the area about the x-axis. Right, the propensity, it's like the propensity of that shape to want to rotate about the x-axis. How easy is it for that geometric shape to rotate about the x-axis? So this is right, the propensity for some torque that we're applying to lead to a rotation. All right, so let's start smashing some things together. So we have y prime fr. Well, this is now p naught y ca. And it's going to get uglier like most derivations. It gets uglier before it gets prettier. So we'll let it get a little ugly. Plus rho g sine theta IXX. So the nice thing about like moments of inertia and like the moment of an area, that's something that you could calculate by doing the integral. Or you can say, like for a circle, somebody's already done that. Let me just look up the answer. For a square, somebody already did that. Let's look up the answer. For an ellipse, somebody did that. Let's look it up. So there, for most common shapes, somebody's already done that. They've already done the hard work. So you don't have to redo it. You don't have to reinvent the wheel. You can just take their answer and say, ta-da, here's the answer. So this is usually something that we look up. But we look it up, so we might be interested, you might be interested in the rotation about, say, like a hinge at the shape's edge. What people have probably calculated and done before is the propensity of that shape to rotate about the center. So you have to figure out, okay, how do we relate like something rotating about the center to rotating about one edge? How are those two things related? So we use what's called the parallel axis theorem. We're not going to do anything more with that other than what we'll do right here. You may have run into this in dynamics class, maybe, statics. Okay, so in statics class, you get this, I, X, hat. So same thing, but with two little hats on it, plus a yc squared. And Ix, the one with the little hats is second moment about the centroidal x-axis. So this is something that's something you would look it up for your specific shape. So there are like tables in your book for different kinds of shape. It's going to be related to the dimensions of that shape. So if you have an ellipse, it's going to be related to the long radius and the short radius, and it's going to be just a pretty simple equation. Maybe it's like 1/12 a cubed b or something like that. So it's going to be related to the different dimensions of that shape, and it's going to be shape specific. So for a square, it's going to be different than a rectangle. It's going to be different than an ellipse, which is going to be different than a donut. Like all of these things will be a little bit different. So you have to find what that is by looking it up. Okay, so now again, let's plug that into, because the hat version that's the one that we can look up. So this would give us, again, it's going to get a little bit ugly, and then it will simplify somewhat. P naught y c a plus, this is rho g sine theta, and then we plug that in now with the little hats, plus a yc squared. Okay, we'll separate that second, multiply that second thing through yc a plus rho g sine theta a yc squared plus rho g sine theta I xx. Okay. And now if you looked, if I gave you a little bit of time to look at it, you'd say this section, this first section here, can actually be simplified quite a bit. This is equal to the resultant force times yc. Right, if you look at it, you can see, okay, there's, right, the resultant force is pressure times area. So you can see like pressure times area. This is pressure and area, but okay, pressure needed one of those YCs. So if you look at it again, you can see, okay, that really is the resultant force times YC. And then this second part, okay, we'll just leave that alone for right now, but that gives us, if we divide both sides by the resultant force, that gives us YC plus, and now we have rho G sine theta over FR. Thanks. Okay, so that's kind of cool. We'll look just to get kind of a sense again of what we're talking about. This is, say, our shape. That's an ugly shape. Get the idea? That's our gate. The centroid of that gate, say it's a circle, the centroid is going to be right there in the center. So that's XC, YC. We have and I'm going to use kind of a number of different colors. We have a linearly increasing, I didn't do this right, but we have a linearly increasing pressure, which is going to lead to a linear, right? It's a distributed load that's linearly increasing as we go down. Our gate, which means like the resultant force is weighted a little bit below the centroid. So it's right, maybe something like there. And if we want to figure out where that is, well, we have, say that dimension is YC. Where we are down here, this is Y prime. The YC plus, it's going to be YC plus a little bit, right? What is it going to be? It's going to be YC plus rho G sine theta I x hat over the resultant force. So this second part, this is that's the extra bit below the centroid. So we always have to be below the centroid because pressure always increases as we go down. So the resultant force, we're always going to have, we have something underwater, there is always going to be a torque applied on that object because there's less force on the top of the object, the shallower part, than there is on the deeper part. And so the resultant force is always going to be acting below the center because pressure is always going up as we go down. So I think that brings us, it looks like it's about 1:50, that brings us to the end of today. There will be a homework posted very soon on Moodle. Our next homework assignment, it's due a week from today. Next week, Wednesday, there's an exam right a week from Friday that we'll talk more about on Friday. So I guess just take note of that if you want to get started on that, get rocking on that early, which maybe you don't, but that's fine, it will be there. Otherwise, hope you guys have a great Wednesday, and we'll see you on Friday.
Do you like exam review stuff?
Yeah, we'll have that, and we'll talk about that Friday.
We're gonna get like a cheat sheet.